Good morning, good afternoon, or good evening, depending when you are. Thank you for coming back to this second week of our school. Today, we have the pleasure to be with Juan Rafael Martínez. He's an staff astrophysicist at the Chandra Xray Science Center and the deputy end-to-end scientist for NASA Chandra Space Observatory Data System. He is based at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. His research interests includes star formation in galaxies and the evolution of star formation history in cosmic time. In particular, he is interested in the physical characterization of the main sequence of star-forming galaxies from the study of the internal condition of the ISM. He uses multi-wavelength photometry and mid-infrared spectroscopy in combination with Bayesian techniques and SED fitting to link global properties of star bursts, such as their star formation rates, with the internal physics of their star-forming regions. Future observations with JWST and the other infrared observatories will greatly benefit from these techniques. He's also interested in time domain astronomy, and he's part of the LSST TBS science collaboration, where he works on machine learning algorithms for light curve classification. He's also interested in infrared astronomical instrumentation, scientific outreach, and education, and he got his PhD in 2012 at the Leiden Observatory. So, Juan Rafael, thank you very much for being with us today, and thank you for accepting the invitation of this school.
Thank you very much, Esteban, for the introduction. And I'm, of course, very happy to be teaching in AstroTwin. I don't think I've actually ever taught in AstroTwin before, which is funny because...
You have the very first year.
Oh, maybe the first
Yes,
year I gave
our
a
first
small,
school. Yes.
I gave a small lecture. Yeah. Anyway,
Yes.
I'm very happy here today, and I am particularly pleased that we've managed to do this despite the current situation. I was originally intending to go in person to Colombia, as you know, but things didn't work out. But I think it's good to do it like this and have a broader audience joining. So I guess we're ready to start. And I don't see my slides. Do you have to? Okay, now I see them. Okay. All right. So so this week's lecture is going to be about data science, astrostatistics, and applications in X-ray astronomy. And I am going to particularly be drawing some experience that I've personally gained and that we as a team have gained over 20 years of operations of the Chandra X-ray Observatory. So I'm really hoping that I'm going to get you some excitement about the possibility of working with X-ray data, about the many interesting things you can do when you work with X-ray data, both in terms of the science and in terms of the statistics and in terms of the data aspects of it, all of which I find particularly interesting. And what you see here is just, to the right, you see the Chandra X-ray Observatory. You see in the left a artistic view of what happens when two neutron stars collide, which, as you know, can be the source of gravitational waves, but also the source of X-ray and high-energy photons that you can detect with a telescope like Chandra. And of course, in the middle, I just have a little plot showing a typical thing that you can do when you do data science, and that's basically classifying objects based on their properties. So I'm hoping that I'm gonna be covering some of this stuff. We have a short time, but I still think we will be able to get a lot covered, and I hope that will be useful for the attendees of the school. So moving on, I'm going to briefly tell you about what this lecture series is about. So it is going to be about astrostats, how we apply statistics to better treat and understand astrophysical data. It is also going to be about data science, how we look for information in catalogs, in astrophysical catalogs, how we combine different catalogs, how we do science with it, using statistics, of course, and using tools like machine learning towards the end of the schools. But it's also going to be a lecture series about X-ray astronomy, at least a very general introduction. So this course will mainly use data acquired with the Chandra X-ray Observatory. That's because I happen to work for such great mission, and I want to convey to you all the excitement about what Chandra can do for you in science. I am not expecting you to know anything about statistics, at least not very advanced topics of statistics. I am not expecting you to know anything about X-ray astronomy at this point, and I am not expecting you to know anything about Chandra. So I hope that I will give you an introduction, so that when you finish this course, you'll be able to right on jump on the data and do some interesting experiments with the data. We will tackle common problems that we deal with in astrophysics when we deal with data, and sometimes even when you are a theoretician, you also deal with these things. For example, what is a model? What is data? How do you best combine data with a particular model, and how you do inference from that combination? How do you measure uncertainty in the quantities that you get in astronomy? Uncertainty quantification is extremely important in astronomy. And I think sometimes it's a little bit disregarded when we actually do science. And of course, I will try to put everything in the context of interesting X-ray sources, so that you don't feel this is only about math and statistics, but you actually put these things in context. And then I will also, try to walk you through a little bit of a philosophical difference between doing frequentist statistics versus doing Bayesian statistics, and what that means, and how we do Bayesian inference in the particular case of X-ray data. But the focus of this whole thing will not be certainly very detailed discussions on the astrophysics, but actually working with data. How do we get data? How do we model data? And in particular in the Poisson regime, because that's the regime, the statistical regime in which we live when we do X-ray astrophysics. So I hope this will be enjoyable. And that was just the general introduction to what will be covered in the next 4 or 5 days. But now I'd like to move to the specific contents of this lecture, today's lecture, and that's going to be a very general introduction to X-ray astronomy with Chandra. So I am going to give you a little bit of an overview on X-rays. What are X-rays? What types of sources in the cosmic context emit X-rays? How do we detect X-rays? How does a X-ray telescope operate to detect X-rays? And I will introduce the Chandra X-ray Observatory, and in particular the ACES instrument, which is one of the 2 instruments that Chandra has on board for science. And towards the end, I will do a little bit of a practical session to show you how to display data from Chandra and how to access the Chandra source catalog. So that's going to be today's lecture. Before I start, let me give you a couple of interesting references that you can try to look at for yourself by yourselves. So the first one is this nice book that was published last year as the pandemic was taking hold. And this is a book that summarizes 20 years of Chandra science. And it was edited by Belinda Wilkes and Wallace Tucker. Belinda was the director of the Chandra X-ray Center until recently. And this book really covers a lot of interesting topics about what Chandra can do, what it has done, what it has discovered, and it will provide you with some context. And on the right, there's the Modern Statistical Methods for Astronomy. This is also a very interesting book if you're more interested in the statistical aspect of things. And in particular, I think it's very good if you're interested in the statistical aspects of things when you are dealing with X-ray data. Eric Feigelson is one of the authors. He is an expert on X-ray astrostatistics, and I'm sure you'll find that book enjoyable. And some of the things that I'll be talking about in these lectures are certainly covered in this very nice book. All right, so let's get up to it. So what are X-rays? Well, X-rays are just a form of light. It's electromagnetic radiation, and it just happens to be of a very small wavelength. So whereas the light that you see with optical telescopes like the Hubble Space Telescope or the Gemini telescopes has, as you see here, wavelengths of something like 10 to the minus 6 meters, which is comparable perhaps to the size of small cells or complex cells. X-rays, on the other hand, are of the order of 10 to the minus 10 meters in terms of its wavelength, and that makes the typical characteristic wavelength of X-rays comparable to the size of individual atoms. And that, of course, has implications for exactly how we detect and how X-rays are produced in the cosmic context. Of course, that is also related to the energy of sources in the sky that emit, as we will see in this lecture. And you basically need to be very energetic or be in an energetic context, being in an environment that boosts up your energy to considerable amounts and your temperatures to very high millions of degrees regime before you can actually produce X-rays. So X-ray astronomy is about high energy astrophysics. It's about the most energetic phenomena in the universe, together, of course, with gamma rays that are even more energetic. X-rays and gamma rays really tell you about the most energetic phenomena in the universe. Here's another view of the scale of photon energy now expressed in electron volts, right? So you see that, for example, so basically the 1 electron volt, as you know, is the amount of energy acquired by an electron if you put it in an electric field of about 1 volt. And that's in principle a small amount of energy. But if you see the range, the logarithmic range of X-rays, and of course, most people are familiar with X-rays because from a medical perspective, but as you can see here, the energy that you typically use for medical purposes is typically in the hard X-ray regimes. When I say hard, I mean X-ray photons that have higher energies, and when I say soft X-ray energies, I mean soft X-rays, I mean X-ray photons that have smaller energies. So as you can see, most of the things you use to do checkouts at airports or do medical scans tend to be of the hard X-rays. In contrast, actually, astronomy lives in the soft X-ray regimes. And I keep forgetting that you actually don't see my cursor because for some reason I cannot show you my cursor here. But basically, the region marked as soft X-rays, that's where astrophysically relevant photons live, at least the ones we can detect with current technology. So that's the range of energies, you know, more or less between half an electron volt, half a kilo electron volt, so about 500 electron volts, all the way to 10,000 electron volts. That's the regime of X-rays, photons that you can detect from astrophysical sources with our current instrumentation. So how were X-rays discovered? Well, as many things in astronomy, this was done, and in science in general, this was done serendipitously. And serendipity is one of those things that I really like about science. In fact, one of the messages I want to convey to you in this lecture series is that there is a lot of serendipitous things that are detected with a telescope like Chandra. In other words, when you look at the region of the sky because you're interested in a particular object, you also detect other sources in that area of the sky. And those can be serendipitous discoveries. They can be a black hole, or they can be a new neutron star, or whatever, and you don't know. And that's why data mining and data science play such an important role in discovery, because you can actually profit from all those serendipitous detections. But before going too far from my main topic here, X-rays were discovered serendipitously by this gentleman here, Wilhelm Conrad Röntgen, who was a German scientist, and he was interested in cathodic rays. So basically electrons. At that point, he didn't know they were electrons, but he knew that if he put a high voltage in the interior of a tube, he would see some rays that would move from the negative cathode to the anode, and those that would actually get accelerated and made it to the glass of this tube will produce that green light that was basically fluorescence of the atoms of the glass when they were hit by the electrons that were being accelerated by the electric field. And he was interested in this rays that were actually electrons. But he said, well, what happens if I actually cover this tube completely in dark board? So I'm going to completely cover it so that this green light cannot escape, and I'm going to see what happens. And what he saw is that even when he covered the tube in this very dark board, some particles or something was still escaping, because he could see fluorescence in a screen that was outside of the tube at 1 or 2 meters away from the tube. And he said, well, this cannot be the light, the green light I'm seeing. This cannot be this cathodic rays or electrons, because I'm completely covering them. So what is it that is producing this emission? He quickly realized this was actually a different type of radiation. And the reason why he gave them the name X-rays is because he didn't have a clue as to what they were, and he called them X. And that's how we have come to know the X-rays today. What was happening, we now know that, is the electrons that were being accelerated in this electric field, when they found that the target, which is that metallic blue cross here in this diagram, they were suddenly deaccelerated, because they would completely hit the wall and be deaccelerated. And we know that electrons that change their acceleration, that lose energy suddenly, have to release that energy in the form of electromagnetic radiation, and that electromagnetic radiation comes in the form of X-rays. So that's how they were discovered by accident, and he quickly realized that they could, pass through things. So he decided to make a photo of the hand of his wife, and this photo that you see there is the first X-ray image used for imaging of the human body. So, of course, every time people discover a new type of radiation, they immediately ask, hey, how can we use this to explore the universe? And so, of course, early in the 20th century, people starting asking themselves, hey, can we actually use X-rays to produce, to study the universe? And again, the problem, of course, or a common problem, I would call it a problem, but it's not really a problem, it's just a fact of reality. We have the atmosphere of our planet, and what you see here is in an upper left plot here is a very typical thing that we show when we try to talk about space telescopes. I mean, that is showing you the amount of opacity, how opaque the atmosphere is to different types of radiation. And as you see there, the atmosphere is very transparent to optical light, very transparent to some wavelengths in the infrared, certainly very, very transparent to radio waves, but extremely opaque to high energy photons such as X-rays and gamma rays. So they are all absorbed by the atmosphere. So if there's an incoming X-ray photon coming from a far away black hole, you're not going to be able to catch it from the ground, because it's going to be absorbed by the atmosphere. And so what does that mean? That people when they started studying the atmosphere, they realized that there was a very high layer of the atmosphere that we now call the ionosphere, that was ionized material, and they knew that something had to be responsible for the ionization of this layer of the atmosphere. Something was hitting the atoms in the upper layer of the atmosphere and making them ionized. And of course, when X-rays came into play, then they started, reasonably expecting that some of the ionizing rays, cosmic rays that were creating the ionosphere, were actually X-rays. And of course, a natural source for X-rays a natural source for X-rays in a cosmic context was the sun. So the sun was kind of the first target of X-ray experiments to try to determine where X-rays were being produced in the universe. But what mechanism, beyond the atmosphere and beyond the sun, what mechanism for production and absorption of X-rays in a cosmic context? And that's an important question, because basically that is going to tell us the physical context in which X-ray photons are produced. And of course, there's basically two types of X-ray emission. It's either thermal or non-thermal. So thermal emission relates to radiation, X-ray radiation, that is being emitted by particles, for example, electrons, that happen to be in thermal equilibrium. So they have a Maxwellian distribution of momenta, and that can happen, for example, in regions like the surface of neutron stars, optically thick accretion disk, etc., etc. What this actually means is that X-rays are being emitted as blackbody radiation directly from these objects, because they are so hot that their peak in the radiation, according to Wien's law, is actually in the X-ray region. So what temperature does it have to have in order to emit blackbody radiation in X-rays? Well, basically, you need to remember that the energy of a photon equals the Planck constant times the frequency of this photon. And if you and in the case of a thermal emission, that approximates the Boltzmann constant times the temperature. And in order to emit at energies of a few kilo electron volts, which, as I showed you before, is the typical range that our X-ray telescopes can detect photons, then the required temperature is of the order of 10 million Kelvin. So imagine this is much hotter than the surface of the sun. This is more like the temperature in the interior of the sun, but also it can be the temperature in the surface of certain stars. For example, neutron stars, they can get that hot, but also the hot plasma that results from the accretion process around a black hole can also have that temperature, and that also emits thermal black holes. And of course, there's also non-thermal radiation. And when we say non-thermal, what we refer to is they are being emitted by particles, again, usually electrons, which have high energies, but whose distribution of momentum is not Maxwellian, as a power law. So basically something that is not in thermodynamical equilibrium, it has a power law. Basically, the higher the higher the energy, the less of those objects emits those energies. And this is mostly of a few types, the non-thermal radiation. So there's a synchrotron emission, that is a relativistic effect of high energy photons moving in the presence of a radiation field. And again, in order to emit non-thermally as a result of synchrotron emission at 10 kilo electron volts, you need you need your magnetic field to feel very, very strong. So for example, the product of the magnetic field times the gamma factor square, where gamma is the Lorentz factor, which is basically the ratio between the speed of the particle and the speed of light, it's at 6 times 10 to the 11. So again, this only happens where there is a very strong magnetic field and high energy electrons and high energy particles are moving in this context. There is also Compton scattering that I will introduce in the next slide, but some examples of regions where non-thermal emission of X-rays happen are supernova remnants. So basically what's left after a massive star explodes, radio galaxies that have strong magnetic fields, cosmic background radiation photons close to giant radio galaxies that provide some of the magnetic fields. In all of those contexts, we have X-ray emission that is non-thermal. And in fact, when you look at objects in a cosmic context, like for example, this ULX, ULX means ultra luminous X-ray source. So these are sources that are extremely luminous in the X-rays. And typically these objects, if you look at the spectrum, the distribution of energies of these objects, they happen to have a combination of both thermal and non-thermal emission. So you have a non-thermal emission that in the plots to the right is the red line that you see in the long energies. It has a very clear power law distribution. And we also have a blue thermal component that typically comes from the plasma, hot plasma, that is basically emitting at those temperatures because it's extremely hot. So when you deal with X-ray sources in the sky, you will have to deal with both of these types, and that's why you have to have it clear. So a little bit more in detail, again, and this is not going to be extremely detailed in terms of the actual physics, but I want you to have an intuition of what we mean. These are a few examples of how non-thermal radiation can be emitted. Of course, I already spoke about the synchrotron radiation. These are basically electrons that are being accelerated and moving in spiral shapes along the lines of magnetic fields in particular contexts, and the acceleration of these objects, the circular acceleration of those objects produces X-rays because those electrons are moving at very high speeds. There's also Compton scattering. So basically this is a context in which there's a low energy photon. For example, think even of photons, radio photons from the cosmic background radiation, or infrared photons that are being emitted by a young star. But if those photons happen to find themselves in a region of high energy electrons, for example, close to a supernova remnant or close to the accretion flow of an object like a black hole, then the electrons that of high energy can pass some of that energy to the X-ray and pass that energy to the low energy photon to convert it into a high energy photon. So it becomes an X-ray photon, and that's what's called Compton scattering. And a lot of the energy, a lot of the X-ray emission that we see, for example, in AGNs, et cetera, comes from this kind of process. And of course, there's also line emission. There's also certain types of atoms that have transition energies between their layers that are of the same energy as certain X-ray photons. So if a atom happens to be excited at that level because it's in an energetic context, and then comes down to the lower energy level, then that will also produce an X-ray emission. Of course, this is only a few cases, perhaps together with the black body radiation, the most common cases of X-ray photons in a cosmic context, but there's more mechanisms that can produce this. And I also want to point out that in very dense regions, for example, if you look at a galaxy, an AGN with a supermassive black hole in the center and an accretion disk and a torus of dust and gas material around it that is very dense, that torus in the context of an AGN can also absorb X-rays. So X-rays can also be absorbed by radiation between you and the source, and that has to be taken into account when you do your modeling. So here's just a few examples of different types of X-ray emission and the astrophysical contexts in which that emission happens. So you have black body radiation. You have that happens, for example, in corona of hot plasma in stars, but also, of course, in the surface of neutron stars. There's also thermal Bremsstrahlung, so basically deaccelerated photons in certain hot gas, for example, in the intergalactic medium between galaxies, in galaxy clusters. Atomic emission can happen in supernova remnants, as we will see a little bit at the end of this lecture. Synchrotron emission happens in any context where there's a rapidly rotating source that has a magnetic field, like in the context of quasars. And inverse Compton happens again in many contexts, in supernova remnants as well, but also in the context anywhere where you have accelerated electrons, for example, in the accretion towards a black hole or a neutron star, where you have photons of lower energy that will also produce Compton X-ray emission. So let's talk a little bit about history of X-rays from space. And of course, I was trying to tell the story in a historical context. So when X-rays were discovered, people were like, okay, let's see what's out there that produces X-rays. And of course, the sun was kind of the first target, but people didn't feel that was enough. They wanted to look for more. And there's a very important figure in the development of X-ray astronomy, and that was Italian-American scientist Riccardo Giacconi. And Riccardo was basically the father in many respects, not the only one, but one of the main figures in the development of X-ray astronomy. He died relatively recently, and he's been kind of a hero for an entire generation of X-ray astronomers. Well, Riccardo was the first one who had the idea to send rockets to space in order to try to detect X-rays from the upper atmosphere. And his first experiments around the 1960s, early 60s or something like that, were basically just as simple. I mean, it was a simple idea, but it was revolutionary in a way. Just put a Geiger counter, so a particle detector, on top of a rocket, send it to space, have it rotate a little bit to try to see if it could detect any X-rays, and then collect those emissions in the Geiger counter. And he did this with this kind of rocket that you see there. I want to point out here, of course, that these detectors were not imaging detectors. There was no optics here. There was no mirror to focus the X-ray emission that was coming from these regions of space. It was only a Geiger detector. The only idea it had about the direction from where this emission was coming was from its own configuration, like where it was looking, and perhaps by rotation of the little Geiger counter when it was up there. And these were typically short flights where it was very short time to calculate. And the plot you see here to the left, in the bottom left, is basically the data that one of those things would collect. And that's basically as it was rotating and moving across the plane of the galaxy and other regions of the sky, it would suddenly detect things like this huge peak that you see there, a huge source of X-ray emission that was the first, extrasolar source of X-rays of X-ray radiation that was discovered by mankind, and it was named Scorpius X1, and this is an interesting object because it's probably apart from the sun, etc., it's the brightest X-ray source in the sky by far. It turns out to be a low mass X-ray binary. This is basically a neutron star that has about half the mass of the sun, and a main sequence star, 1.5 times the mass of the sun, that is orbiting that star. And the main sequence star is passing material onto the compact object, the neutron star, and that accretion process, as I have mentioned before, produces X-rays. But this source is so bright that we haven't even looked at it again. I mean, we don't look at it with Chandra because it's so bright that it can basically completely break the detector. So that's a reason why we don't look at that source again. All right. So, but that's not the only kind of X-ray source that was originally detected. There was also quasars. So these are active galactic nuclei very far away from us. And a lot of other X-ray binaries were detected by these early experiments of X-rays from space. So one of the early mysteries that this resolved was the issue of X-ray emitting stars. So ever since in 1967, Jocelyn Bell had discovered pulsars that were very rapidly rotating stars, neutron stars, people knew that they could be sources of X-ray energy. And by the way, one very massive example of X-ray emission from a pulsar is the beautiful Chandra image that you see of the Crab Nebula here on the bottom left, where basically the source of all those X-ray emission is basically a very rapidly rotating neutron star in the center. But people were wondering, is this the only way in which these things can be produced, or are there other ways in which stars can emit X-rays? And of course, the other possible explanation was what I just said before, X-ray binary. So a very compact object that you see here on the upper left, a very compact object accreting material from a companion star, and that accretion process accelerates electrons to a level that can produce X-rays in the mechanisms we have mentioned. And actually, with the launch of the Uhuru telescope in 1970, this was another sophisticated case of a counter. This was still not an imaging telescope. This was just a counter, but it was the first one who could, by looking at the distribution of energies of these X-rays, was actually able to determine that accretion processes, like what happens in the case of a X-ray binary, were responsible for a significant amount of the X-rays that were being detected. However, this was still not an imaging telescope, and we had to wait almost another 10 years until 78 before an actual telescope, an X-ray telescope, was put in space. So one other interesting situation, I was just mentioning to you that very bright source, Scorpius X1. It's a very, very luminous object. And there are many other very luminous objects in the X-ray sky that pose a very interesting question for us. And that has to do with physics, and that has to do with the Eddington limit. So basically, what happens here is that when an electron scatters a photon, it absorbs momentum from the electromagnetic wave, as we said before with the quantum scattering. And what that means is that there is a radiation pressure that is basically the X-rays that get formed by this quantum process produce radiation pressure outwards that tend to counteract the accretion process. So material is trying to fall inside, for example, a black hole, but there's also a lot of X-ray emission and quantum scattering that is happening, and that produces an outwards force. And there is a point of equilibrium in which the radiation pressure of the X-rays and other types of emission equals the gravitational pull that tries to accrete material into the compact object. And you see here in the bottom, you see expressions for the amount of energy related to the gravitational pull of the gravitational field, and also the energy of the radiation pressure that relates to the luminosity of the object. And so there's a point where those two quantities are equal to each other. And that means that in principle, the object will stop accreting, because basically the accretion is exactly counterbalanced by the radiation pressure. And that happens at luminosities, X-ray luminosities, for a star which is about the size of our sun. That happens at about 10 to the 38, 10 to the 39 ergs per second, which basically means that if you see objects that emit at luminosities that are beyond that Eddington limit, you either need to have a much more massive central object, so a massive black hole much larger than a star, or there has to be mechanisms that explain why we see a luminosity that seems to exceed the Eddington limit. Just to say it again, you don't expect, if that's a compact object that is accreting, right? And you're seeing X-ray emission that you assume comes from accreting, then there is a limit for a given mass of the central object. There's a limit for that luminosity, because beyond that luminosity, the accretion would stop and you should not be seeing X-rays, but you still see them. So either the central object is more massive than you're assuming, or there is another mechanism that is allowing the system to produce X-rays at those great luminosities. All right, and that's at the center of the explanation for what ULX are. ULXs are these very massive objects, that very luminous objects, some of which are actually candidates for being intermediate mass black holes. So we know they are not supermassive black holes because they don't live in the center of galaxies. You see here, as in this case to the left, in the M51 galaxy, there's a ULX there that is offset from the nucleus of the galaxy. So this is not likely to be a supermassive black hole like the one in center of galaxies, but it's very luminous. So it might be an intermediate mass black hole, or it might be something else. So these are some of the questions that, despite the launch of all these telescopes, remain open. And those are the kind of questions that we're trying to answer with X-ray astronomy. So I was mentioning before, all these objects discovered these original very bright sources in the X-ray sky were actually not imaging telescopes. They were detectors placed on top of a rocket or put in a satellite to orbit the sky. But in 1978, the first imaging telescope was launched to space by NASA, and that was the Einstein Observatory. This was the first satellite that had a set of mirrors, and I will talk a little bit about mirrors later today. But it was the first satellite to have an optical system that was able to focus X-rays and put them into a detector in order to have images of the sky. So the first X-ray images of cosmic sources came from Einstein. And you see here in the bottom left, you see an image of a supernova remnant called W28. Again, this is basically what is left after a massive explosion. Thermonuclear explosion happens at the end of a massive star's life, and that produces a whole lot of X-rays. And you see the distribution of those shocked. This is a lot of shock material. The explosion produces a shock, an explosion shock, and that excites certain types of atoms that also produce X-ray by fluorescence, etc., etc. So you see a complex image, and Einstein was the first one to actually make those images of these kind of sources in the sky. And just for comparison, that little stripe you see there is actually a similar image, a similar region of the sky in that same area of the sky, but imaged with Chandra. So you see the difference between the early telescope and what we're able to do with Chandra these days. And what's interesting as well is that it's not only supernova remnants that emit these X-rays in an extended fashion. There's also things like very, very, dense and dense gas between dense and diffuse gas between galaxies in galaxy clusters. That gas cools down because of the dynamical interactions between the galaxies of the cluster, and that also emits X-rays. And we can see those extended structures, and that was only possible when we actually were able to focus X-rays using mirrors. So this sets the scene for the appearance of the Chandra X-ray Observatory. Basically, after the discovery of the first extrasolar X-ray source, the year after, Mr. Riccardo Giacconi, that I have introduced before, wrote a white paper saying, hey, we need to build a big X-ray telescope in space. And it took another 8 years or so before, 7 years or so before him, together with Tannenbaum and others. Tannenbaum was the first director of the Chandra X-ray Center, proposed this to NASA to build a 1.2 meter X-ray telescope that was a successor to Einstein, but at a much bigger resolution, an angular resolution less than half an arc second, very high sensitivity, very high quantum efficiency, which meant it had to be a telescope with extremely good eye, able to resolve very small details in the sky, but also able to detect X-ray photons. I mean, something that I have not mentioned yet in this lecture is X-ray photons are very hard to detect because they are not produced in huge quantities like optical photons. When you think of optical astronomy, you think of a stream of photons that comes in you, and you only measure the flux of it. Whereas in X-ray astronomy, you actually detect individual photons. There are individual photon particles that are hitting your detector, And that's why statistics in the context of this lecture are so important. We live in the Poisson regime. We are going to do statistics with individual photon arrivals. And that's why this is so important. So this was a great proposal. And in 1977, NASA adopts what was originally called the Advanced X-ray Astrophysics Facility, EXAF, was the original name for the Chandra X-ray Observatory. And in the Decadal Survey of 1980, the Decadal Survey is this big meeting of many panels of experts that every 10 years get together to advise NASA and the National Science Foundation as to what needs to be built for astronomy in the next 10 years. They recommended Chandra or EXAF in the 1980 Decadal Survey. By the way, we just had a Decadal Survey again. It was supposed to happen last year, but because of the pandemic, it actually happened this year. And the results were released. And one of the recommendations, even though it was not the main recommendation of the panels, was to build a successor, an even more advanced X-ray telescope that it's called LYNX. And LYNX will be the next generation X-ray telescope. Anyway, time happened, and just for you to have an idea of how long these processes can be, from 1963, that was the original concept by Giacconi, only 35 years later, we could actually get ready for launch. And that happened in 1999 when Chandra was launched from Cape Canaveral on board the Space Shuttle Columbia. And the commander of that mission was the first female commander of a NASA Space Shuttle flight, and that was Eileen Collins. Eileen Collins was here with us in Cambridge to celebrate 20 years of Chandra a couple of years ago, and she told us about all the adventures of putting this wonderful telescope into space. This is the Chandra X-ray Observatory at a glance. On the left, you see a photo of Chandra before launch. It's a long tube, and you will see why it has to be a long tube soon. But basically, what it has is it's in reality it's a very simple system, and it's basically a set of mirrors, the high resolution mirror assembly. And some electronics for powering the solar panels, etc., an antenna for communication, several antennas for communications, a sunshade. Chandra, it's in a very elliptical orbit around the Earth. The reason why you want to put this telescope in a very elliptical orbit around Earth is because you want to avoid the radiation fields produced by the magnetic field of our planet, because that's going to be extremely dangerous for the detectors, etc. So you actually close this shield when you're crossing, when you're in the closest point of the orbit to Earth. You keep this shut down so that the detectors and the optics don't get affected by those radiation fields. And Chandra only observes when it's actually far away from the Earth, closer to the apogee of its orbit. And on the other side of the tube, you have the instruments. And the two main instruments here are the high-resolution camera and the advanced CCD imaging spectrometer, ACES. And I will describe them a little bit in more detail later. But those are the two instruments that that live in the focal plane, where the mirrors focus the light, the X-ray light coming into the telescope. How does this work? I'm not going to be extremely detailed here, but in order for an imaging telescope to exist, you have to be very clever. The reason is that it is very hard to make X-ray photons reflect in a surface. That's because they're so energetic that they tend to completely pass through surfaces and rather be dispersed or even absorbed rather than reflected. And so what happens is that if you just start from first principles, where you have the refraction coefficient of a material that's given by this quantity n, and n has a real part and an imaginary part. The imaginary part, I times beta, mostly deals with absorption of X-rays, and the real part, delta, which depends on basically the density of the material, as you see there. The radius of an electron, remember that X-rays are about this, the wavelength of an X-ray is about the size of an atom. So it's actually the atomic structure that determines the optical properties of X-ray, optics. And of course, the wavelength corresponding to the X-ray regime. So if you just apply the Snell law, the optical Snell law that tells you, that directs the optics of reflection and refraction, etc., and you apply that to this coefficient, the thing is that that index of refraction, happens to be very, very small for solid materials, for X-ray wavelengths. So these are extremely small quantities, which means that if you calculate from Snell's law the critical angle at which you will have total reflection, at which, in other words, if you use Snell law to calculate the angle that you would need to completely reflect X-rays rather than have them absorbed, that angle happens to be very, very small. Is basically given, that critical angle is given by the square root of 2 times delta, and that happens to be for X-rays and typical solid materials, that happens to be less than 1 degree. What this means is that if you want to be able to make X-rays reflect in a mirror and focus, you cannot use the typical things that you would use in optical astronomy, where you have a parabolic mirror, because X-rays would tend, at high incidence angles, they would tend to pass through the mirror, and you don't want that. So you have to make them hit the mirror at very, very low angles, less than 1 degree. And you can think of it as when you go to the lake and you throw a little stone to make it bounce on the water. That's basically what you have to do. You want to make sure that you throw that little pebble at a very small angle so that it will jump off the surface of the water. That's exactly what you do here with X-rays. And in the right, you see how that's accomplished. Mirrors in X-ray astronomy are actually this, the configuration is the surface. It's actually the interior of some kind of tube structure that guarantees that X-rays will hit the reflectors at a very small angle and then focus on this focal plane, which for Chandra, that focal plane distance is about 10 meters, and actually you form an image and focus the photons there. So I will not extend much further regarding reflection. All I want to tell you here is that for you to have efficient reflection, and you remember that quantity delta depends on the density of the material. In particular, it actually depends on the electron density of that material. And so you want your X-ray reflecting surface to be of a very heavy material. So for example, gold is a very interesting material to have your mirrors coated with, so that they reflect efficiently the X-rays. And current X-ray telescopes, including Chandra, have energy ranges between 0.1 and 10 kilo electron volts, as I had mentioned before, and grazing angles between 0.5 and 1 degree. And again, the way in which you make that happen is the geometrical figure that you use to construct the shape of those telescopes, of those tubes. So this would be kind of a side view of one of those tubes, this yellow line here that you see marked with reflection surface. That's basically a segment of a parabola. And that parabola, but of course you don't do that close to the focus. You do that away from the focus, so that the incident angle of the photons is small. And as long as the incident photons are parallel to the axis of this parabola, all photons will focus on the focal point of the parabola. It doesn't matter where they hit the reflecting surface. The problem is when they are not parallel, as you see in the bottom. When you have X-ray photons that are not parallel to each other, for example, because they come from outside of your field of view. In every telescope you will have a field of view, and photons that come from the outskirts of that point of view will not necessarily reflect and focus on the same focal point as photons that are aligned with the optical axis of the telescope. And that means that you have a coma effect that will spread the point spread function. For those of you that don't know what the point spread function is basically the shape that describes the response, the optical response of the telescope to a point source. So a point source doesn't look like a point in a telescope. It has an extension, and that extension is given by the point spread function. And that point spread function, because of this coma effect outside of the optical axis in X-ray telescopes, is particularly, strong, that coma effect. And that means that as you move away from the center of your image, as you move away from the center of your X-ray optical axis, you will have a much larger degraded PSF. And that's exactly what happens with Chandra. And as you can see here, you see here basically observed, actually I think these are simulated point spread functions for Chandra. And as you move to the right, you will be farther away from the optical axis. So you see that the PSFs become larger, and the effect of that is that when you're far from the optical axis, so far from the center of your X-ray image, your resolution is much smaller, because you are not able to distinguish things that are very close together, because basically your PSF will be so degraded that you will not be able to do that. And that also depends a little bit on the energy. I mean, the specific shape of the PSF depends on the energy of the X-ray photons, as you see here on the vertical axis here. All right, so this is just to give you an idea of the different types of configurations that you want to have for this telescope. In reality, what you do in practice is you have both a paraboloid and a hyperboloid surfaces, and you put them together, and you have telescopes that follow a hyperbola, and you have you have reflecting surfaces that follow the hyperbola, and you also have reflecting surfaces that follow the parabola, and you put them together so that you try to find a good compromise between the aperture of your telescope, how big the aperture of the telescope is, and how far your focal distance is. And basically the most used one, including for Chandra, is the type 1, because in that case you get the shortest focal length to aperture radio. So basically you want to have the largest aperture possible, so you collect more photons without having to use a very long tube to focus, because otherwise you cannot fit your tube in your rocket and you cannot send it to space. So the Volter type 1 configuration typically gives the shortest focal length to aperture ratio, and that's what it's actually done mostly in telescopes like Chandra. So this is just basically, again, how it works for the particular case of Chandra, and then basically the focal length and the collecting area will depend on your aperture radius R and your focal length, etc. Et sorry, and basically the length LP is the length basically covered by the array of the telescopes. The way this actually looks in 3D is something like this. They are nested mirrors. They are tubes that are concentric to each other, and that's how you actually build it. And of course, you have to realize that here the area that astronomical sources see, as they see the telescope, is not equal to the total area of the mirrors, because they are so inclined. They have such a big inclination for the grazing angle that the effective area needs to be calculated based on those inclinations, and you actually have an effective area, aperture area, and that effective aperture area, we try to maximize it, of course, by having this kind of nested configuration of mirrors. Okay, that's about mirrors. What about detectors? So, of course, one thing is to detect, to focus your X-ray light, but now you need to make sure that you detected. So you have a optical system like your crystalline and your iris in your eye, and then you have a detector that would be your retina or retina. I don't know how you say that in English actually, but anyway, you also need a detecting a device. And of course, you would want this device to have very high spatial resolution, good energy resolution, good temporal resolution. Why is energy and temporal resolution so important in X-ray astronomy? It's precisely because of what I said before. We are detecting individual X-ray photons. We are not detecting a flux. I mean, it's not like you're throwing a stream of water. Don't think of it as a river of photons coming into you. Think of it as a leakage, as a little small, droplet by droplet kind of situation when you're detecting individual incoming photons. So you want your detector to be able to detect, to know the energy of those photons individually, and you also want to know when those photons arrive, because that's, as we will see in these lectures, that's important for spectroscopy in X-ray, and that's important for time variability. You want to be able to know whether an object that emits X-ray in a cosmic context is actually variable or not. So, but the perfect detector, of course, does not exist, and so we have to come up with the best possible thing we can do. And basically, again, we have the imaging and not imaging detectors. Imaging detectors, of course, are able to actually form the image that has been focused by the optical system, whereas non-imaging detectors don't have very good resolution. It just tell you they can get a focus image from the optical system, but still will not have the resolution to tell you that. And so, and the things you want to collect from every single arrival photon is the energy, the arrival time, number of detections, the position where in the detector it fell, and in some cases also the polarization, of course. But of course, this is not always an easy task, and you need to balance between those three things. So, for example, if you think only of time resolution, it can happen that two X-ray photons hit the detector in a similar location in the same resolution element of the detector, so close in time to each other that you cannot know whether they are actually two different photons, and you can assume it's a single photon, and that's called pile-up. And pile-up can be a problem in very energetic luminous X-ray sources. So there's ways to mitigate that, but it's a complicated issue. So you want the time resolution of your detector to be good enough to try to reduce the pileup. Same goes for energy. I mean, can you distinguish between two energies? And that will have to do, in the case of CCD detectors, with how sensitive you are to the energy gap. How fine your energy gap of your detector can be finely tuned in order to detect X-ray photons that are of different energies. So there's two types of detectors that are actually used in Chandra. The first type, and the high resolution camera, the first of the Chandra instruments, uses this type of detector, is a microchannel plate. And a microchannel plate is basically a collection of individual tubes that are covered inside with something that is sensible to photoelectric effect. So basically what you happen is each photon that enters a particular tube, and these tubes are distributed in an array so that you have some sensitivity, some spatial information. So basically, you know where in which of the tubes the photon first entered, and so you know the position in the sky from where it was coming. And then what happens is that basically the photoelectric effect will do is it will produce a cascade of electrons. Every time an X-ray photon enters, it will produce photoelectrons from the surface of this thing, and that will hit the walls of the tube internally, as you see in the bottom right, and those will in their place produce more electrons, and then you have a cascade of electrons that were formed by a single arrival of X-ray photon. And of course, you can gain some information about the energy regarding the energy of this photon by measuring the amount of photoelectric photons that you collect, etc., but also the intensity. So that's how microchannel plates work. The problem is that, of course, at very high energies, beyond 10 kilo electron volts, and that's one of the reasons why X-ray telescopes typically don't observe beyond that range. This becomes very efficient because even for this microchannel plate with very high photoelectric yields, these X-ray photons are so energetic that they tend not to produce these cascades. They just pass through. And basically, this is important. This is basically the typical. I've been talking about X-ray astronomy today, but this is supposed to be also a lecture on data, and the actual way on which you get your data in X-ray data is what it's called an event file. And an event file is just a list. It's just a list of individual photon arrivals for which you collect the time of arrival, the position of that arrival. In the case of the microchannel plate, is basically which of the tubes it fell on, and then typically also the energy. Microchannel plates are not very good at distinguishing between different energies. They have some information about energy, but not so much. But that's typically the things you record, and they are recorded in this format. It's basically an event file. It's basically a list of individual photon detections on which you have all the information you need for each of those photon arrivals. What the other approach, of course, for detection of X-rays are charged coupled devices, CCDs. These are very common types of detectors based on semiconductors and solid-state detectors. And of course, again, this is not a detection of light course, so I will not go into details here. But basically, what you do is you have a semiconducting material that has a depletion region. So basically, for example, a p-type semiconductor, which is doped with a material that, for example, has one electron. So it's basically silicon, but you dope it with a few atoms of an element that it's slightly heavier than silicon. So it has one extra electron in the valence band, and that extra electron, when you apply a voltage, tends to segregate, and then it leaves a bunch of holes or excess of charge in this depleted region. And because these are electrons that live in the valence band of these 8 atoms, but are not strictly attached to any of the bonds between atoms, they are very easily to excite. So basically, there is a gap between the valence and the conduction band, as you see here. And basically, if the atom structure is rigid, if it's not doped, if it's not a semiconductor, then the energy you need to make an electron move into the conduction band where it can be carried by an electric field, it's large. You need a lot of energy to do it. But if you dope the material, then because those extra electrons are attached to the atoms, but in a loose way, then you can reduce the amount of energy that you need to apply in order to make it move into the conduction band. And by tuning that amount of doping, etc., and other optical properties and physical properties of your semiconductor, you can tune that energy. So you can use CCDs to detect X-rays as well. And that's actually what ACES uses. The advanced camera of Chandra uses a CCD detector, and this is basically an array of different pixels, each of which is basically a semiconductor that will give you the information about the photon arrival. So this is, again, the optics of Chandra. As for the detectors, as I've mentioned, there's 2 cameras, ACES, which is a CCD, and HSE, which is a microchannel plate. It also has gratings because you can do high-resolution spectra with Chandra, and I will not be talking about high-resolution spectroscopy with Chandra in these lectures, but that's another thing you can do with Chandra. Some other interesting facts about Chandra: it orbits Earth every 64 hours. And it goes about 1/3 of the distance to the moon when it gets at its farthest point in its orbit. And it's got a very, very supreme resolution. In fact, Chandra continues to be the best resolving X-ray telescope which is currently in use, beyond anything that existed before. and beyond anything that still exists, like the European counterpart, the XMM Newton telescope. So this is a superb machine that it's still doing excellent work, and it's still alive, and it's still producing great science. This is the way in which the detectors are disposed in the arranged in the focal plane, and there's 10 of these chips. Each of those chips, it's basically a CCD array, and there's 2 sets of detectors that Chandra uses to do the science. So in most of the images, you'll see basically that when you place the focal plane in the sky, you will get an image on each of these individual chips of a slightly different region of the sky. All right, so I told you about the fact that Chandra, the typical output of a Chandra observation is an event file. What is an event file? An event file is basically a list of arrivals, of individual photon arrivals into your detector. And that can only be produced after a number of calibrations happen. I mean, it's not easy to produce an event file. You first need to calibrate for the energy of the photons. You need to calibrate for the time resolution of the telescope. And one very important thing, Chandra is constantly moving as it takes an observation. It's not static, collecting it's not that you point the telescope to a particular location and wait for the photons to collect. You're actually moving, you're dithering the telescope as you move in a particular pattern, because that improves resolution, because that makes it less likely for the detector to break up, etc., etc. But what that means is that what you actually see in your detector is a very distorted version of the sky, because you're moving the telescope as you detect, so the detector is moving with respect to the sky. And what you see, it's actually on your detector initially, is more like what you see here on the right of this bottom plot here, where you see something that looks like a square with a bunch of bright points. And the bright points are basically where the source was, but because you were moving the detector, you kind of completely screw up the actual shape of that source. So you need to do something called the aspect solution. The aspect solution is it's an algorithm that will tell you, okay, this is how the telescope was moving, and we are going to reconstruct the image from the detected photons into an image that actually looks like the one on the left here, like a point source in this case. So there's a lot of calibration, very detailed, important calibrations to do before you have an event file. But eventually you get to an event file, and the event file is going to be just a list. Again, in the case of Chandra ACES, is going to be a list that of events. That's why it's called an event file. And an event is the detection of a single X-ray photon. So you have a time, you have the time of arrival, you have to know in which CCD it fell, the position in X and Y, the energy, etc., etc. So these are all quantities that are recorded in an event file. And when you actually get data from Chandra, either because you are the observer who requested the observation, or because you're looking at archival data. And let me mention at this point that anyone can access the Chandra archive. That's what we're gonna be doing very soon, and actually get images or data from Chandra and event files and do science with them. And again, let me mention that word again, serendipity. A lot of the sources that we've detected with Chandra have never been studied in detail, because many of them were serendipitous detections. No one was expecting to detect them, but we did detect them because they were on the field of another observation, but no one has taken the work of actually looking at those sources. So anyway, you can be the first ones to do that in case you're interested. So after you follow these lectures, maybe you'll be able to make many X-ray discoveries. All right. So, I wanted to mention here, I put it in red. An event file is not an image. So we're used to getting images from our telescopes, right? You basically have so many photons that you actually have fluxes incident in your detectors, and you can form images. That's not the case for X-rays, of course. We have individual photon arrivals, and we know where the detector hit where the photon hit the detector. We know the time when it arrived, and so we have to actually reconstruct an image from that event list. And so when you see an image like this, and this is the Cassiopeia A supernova remnant, one of the most beautiful sources in the X-ray X-ray world, you see that this is an image that's actually been reconstructed from the event files that were produced by Chandra. And the way Chandra observes is it observes in different, it basically, because it collects the energy of every single photon, you can break this apart into different energy bands, right? That's why ACES is, it's called the Advanced Camera Imaging Spectrometer, is because this is also spectrometer. You don't need a dispersive element to do a spectroscopy, at least low resolution spectroscopy, for the simple reason that you are collecting the single energy of every photon that hits your detector. So you have information about the spectral distribution of energies right from your event file. And so you can also break that into different bands, and each band gives you different information about the physical system you're observing. So Chandra, you can, for example, all of the quantities that are estimated for Chandra observations are actually given for a number of energy bands. So it's either the ultra soft band between 0.2 and 0.5 kilo electron volts. This band is not so useful anymore because over the years Chandra has been degrading, and the spectral response to certain energies is not as good as it was when the telescope was launched. So you can still use it, but you have to be extremely careful in interpreting the results for very low energy photons that are detected by Chandra. But then we also have the soft band that goes from 0.5 to 1.2 kilo electron volts, the medium band from 1.2 to 2, and the hard band between 2 and 7 or 8 kilo electron volts. And each of those bands, of course, give us different information about different types of objects. So, for example, if you look at the spectrum of this supernova remnant, the Cassiopeia supernova remnant that you see here on the bottom left, you see that different emission lines correspond to different energy bands. And so, for example, you'll have certain of these lines are produced by recombination of excited atoms. Some of these lines will be produced by shocks as the shock wave from the supernova remnant crosses certain regions of the plasma. And so by separating these lines into energies, then you can learn about where those physical processes are happening. That's what's happening here on the left, on the right. Sorry, that's basically your reconstructed image, but you're breaking it apart into different energy bands, with red corresponding to the to the soft band, green corresponding to the medium band, and blue corresponding to the hard, the most energetic photons that Chandra can detect. Again, these are not the most energetic X-ray photons that can be detected from space. In fact, Chandra's optics and detector physics limits the amount, the energies of photons to about 8 or 9 kilo electron volts. But beyond that, you can look at higher energies, for example, with other observatories like NuSTAR, which actually have detectors and optics that allow to detect X-ray photons beyond the 10 kilo electron volt limit. But 10 kilo electron volts is certainly a hard limit for Chandra, and that's why you see here. All right. So what I want to do, I think I've covered most of what I wanted to cover on today's lecture from the kind of lecturing point of view. What I want to show you now is, after a short break, is I want to show you a little example of how to retrieve data from Chandra. This is, again, a course on data science. And so we're going to be dealing with data, and I want you to be able to retrieve data from Chandra, from the Chandra archive, and hopefully be able to play with it yourselves at home. So we're going to use a couple of things. I'm going to show you how to retrieve data from the Chandra archive. I'm going to show you how to retrieve data using chow commands. Chow is the software that we use, that we developed and that we use to analyze X-ray data here at the Chandra X-ray Center. And then I will also show you how to access the Chandra source catalog, and how to do that from a Jupyter notebook, and how you can actually get interesting properties from X-ray sources straight into your Jupyter notebook session and do science with it. So that's what we are going to do in the next short practical session after a 5-minute break. But I guess at this point, people would want to take a short break.
Thanks, Juan Rafael. Before the break, I would like to tell you that you have a couple of questions in the chat. You want to answer them now, or you rather prefer later after the break?
Sure, let's do it now.
Okay, so the first question is, it's related with some other comment that says, in the part of the mechanism to the production of an absorption, why do we not use the Planck distribution to talk about the distribution that X-rays follow, but we use the Maxwellian one when we talk about thermal emission?
That's a good question, and I guess the answer probably is related to the fact that at the temperatures and energies that electrons have in the typical astrophysical context that we're dealing with here, a Maxwellian distribution of energies is a good enough approximation of what the energies, how the energies are distributed. And again, this will depend on a lot of things. This will depend on whether you need to account for relativistic effects, etc., etc. But typically, I only used the Maxwellian distribution as an approximate way to describe the energies of the not even the thermal photons, the thermal particles that are actually producing the emission. So it's not really the photons here. When we're talking about the photons, we're talking about the particles that produce that emission. And these particles that are in thermodynamical equilibrium, for example, in the surface of a neutron star, those are well described in general by a Maxwellian distribution.
Okay, thanks. Next question says, how will the next generation of X-ray detectors, e.g. links, improve upon the current Chandra design?
That's a great question. We just had a very stressful few months waiting for the results of the decadal survey. Of course, here at the Chandra X-ray Center, we were rooting for LINX. LINX was designed by a team of people here, and it's an excellent instrument. It's an excellent instrument. It has the advantage also that it's cheaper, despite being an absolutely wonderful machine. It's cheaper than other concepts for optical astronomy. And it also has a good chance to discover things like, for example, what happens during a kilonova explosion. I mean, there's a lot of interesting links with gravitational wave astronomy there. So we were rooting for it. It was selected as a second priority. So the first priority will be LUVOIR. The first priority will be LUVOIR, which is kind of an enhanced Hubble. Basically, the way in which LINX improves Chandra is collecting effective area and detector quality. So resolution is going to be improved, sensitivity is going to be improved, and also quantum efficiency and other things that will improve, all those things I was mentioning in terms of energy resolution, time resolution, etc., etc. So that's how LINX, it's an improved version of Chandra. It actually doesn't require a whole lot of new technological developments. It requires some, but not extremely risky ones. And so it's basically a boost of the Chandra thing to make it even more robust. One thing I did not mention during this lecture yet was Chandra and LINX and XMM Newton which is the European X-ray telescope, are all telescopes that are targeted telescopes. So they look at a particular region of the sky at each time. So they target specific objects in the sky, and they are not all sky surveys. But for people interested in all sky surveys in X-ray astronomy, there's also a telescope that is doing that, and that's the eRosita. And I will mention eRosita, I think, in lecture 3 when I talk about variability, or lecture 4, I don't remember. But there's also a way to map the entire sky in X-rays. And there's telescopes that are doing that. But neither Chandra or Lynx are that type of telescope.
Next question. All pulsars are binary systems, neutron star plus main sequence companion?
No, not all pulsars are binaries. In fact, pulsars are mostly powered by their own rotation and magnetic field. There are, of course, cases where a pulsar also happens to be a binary. But that was actually the big question before the launch of Uhuru, which was one of the big first satellites for X-ray astronomy. Is the rotation of a pulsar and the blackbody emission from a pulsar enough to explain all the X-ray emission we're seeing from stars? And then it was realized that it was not enough, that you needed binary systems to do it. But no, not all pulsars are binary.
Okay. Next question. Is the exposition or integration time reduced by using these new constructive techniques, or are more related to sensitivity of the instrument?
So I guess Jorge is asking about the integration times for a particular observation, and whether, and I don't know which new constructive techniques you're referring to, maybe the ones for Lynx. Yes, I mean, of course, we want to make telescopes more efficient at collecting data. One problem with Chandra, which is starting to be an old machine now, it's still in excellent health, but it starts to have certain limitations. For example, the detectors, you cannot expose the detectors for too long now, because you might burn the electronics. So now we separate observations in shorted integration times and in shorted exposures. So before we could expose for, I don't know, say 8 kiloseconds or something at a go. Now we have to do bunches of 3 kiloseconds for each observation, because you don't want to keep the telescope exposed for such a long time. And that has limitations also in the way in which we schedule observations. I mean, a big part of what we do here at the Chandra X-ray Center is actually schedule the observations to match not only the scientific requirements of the observer, but also to match the limitations that the instrument has, and also to match the radiation hazards that come from when the telescope is closer to the Earth. So it's a very complex system, and sometimes we have to split observations in several parts. So that's all going to improve with Lynx, of course, but it's a very tricky business, as you can imagine.
Yeah, definitely. Because also,
how do CMB photons become X-rays?
When they happen to cross very strong regions of strong radio galaxies, where electrons are accelerated to very, very strong speeds, and have enough energy to turn something that has wavelengths typical of the radio cosmic backray radiation into X-ray photons.
Okay, so how does Chandra deal with X-ray radiation coming from our sun? How is it avoided or treated?
Well, it never looks at it, basically, and it's the electronics. I mean, the telescope is not static in its orbit. The telescope can rotate. The telescope can point in different directions. And of course, part of what we do in order to make sure that Chandra's electronics are kept healthy is by never exposing the electronics to the emission from the sun. In that context, the radiation from the magnetic fields around the Earth, which are basically, emission from the sun that gets trapped into the magnetic field of the Earth, is the real threat. And that's when we close the telescope to make sure nothing happens. So in those moments, we don't observe with Chandra.
Okay. Why are the softer bands not as good as they were when Chandra was launched?
Because we've lost spectral response in that regime. Basically, the CCDs, as they are used, as they are heated, etc., etc. I was telling you about the CCD detector. Of course, this is not a course on detection of light, but your ability to tune the energy in order to detect an electron of a particular energy, to detect a photon of a particular energy, depends, of course, on the physical properties of the substrate you're using, your semiconductor. And when that has been heated many times, etc., etc., you lose that capability to detect that those very smaller energies, because now that energy gap has kind of closed, and you cannot do that. You need a slightly higher energy in order to excite the photons. Sorry, to excite the electrons in the CCD array. So that's basically why it's aged. It's been heated up many times, and that reduces the quality of the CCD semiconductor array.
Okay, I think that was the last question here on the chat. You have many congratulations on the different people that is telling you in the chat. Great talk, thanks, awesome. So we will be back in 10 minutes. Do you think that the next part of the session will be covered shortly?
I think so. I mean, I have material for more, but I will cover some of that tomorrow as well. So yeah, let's meet in 10 minutes. And those of you who want to stay slightly longer afterwards, maybe we can do that, but not too much longer. So maybe half an hour in total is what I need. So we'll see.
Okay, perfect. So Juan Rafael and I will turn off our cameras and our speakers and microphones, and then we will be back here in 10 minutes. So 11:40 in our Colombia time, and you have to make your calculations based on GMT -5. See you in a couple of minutes.
2 weeks ago. I should ask.
Okay, thank you for this break. Let's continue with the talk of today. Well, the lecture of today. This is not only a talk, it is a lecture. In the chat, I will pass you a link that you can also find on the webpage of the school, where you can find all the material that Juan Rafael will be sharing with us today and will be using as part of the lectures that he is giving us. Juan, the space is yours again.
Yeah.
Thank you, Esteban. Can you hear me?
Yes, I can hear you perfectly.
Okay, so yeah, okay, so we have half an hour. So there's a couple of things I want to show you. The first thing is how to retrieve data from the Chandra data archive, and there's actually there's a lot of ways in which you can do that. The Chandra data archive is a very complex beast. It basically collects. So the way this works is when astronomers request an observation with Chandra, so there's a panel that decides who gets time and who doesn't. So usually the most scientifically interesting, observations are granted. In fact, not really. I mean, there's been a historical bias in this process of selection against minorities, young people, and women. Luckily, that is changing. So NASA now uses a double-blind system for panels. So, for example, when you sit on a panel, and I actually participated in the last two panels, and the last one was the first one that was done double-blinded. You don't know who's submitting the proposal, and that has increased the number of time granted to young researchers and to women. So that's an excellent move forward, but we still have to improve it. But the point I was trying to make here is that once you get your observations, typically the data is yours and only yours, and yours and of your collaborators for a period that it's called a proprietary time, and the proprietary time is typically 1 year. But that's also changing, because I think something that is becoming very, very clear is that open data, open source code, and open research is the best, most effective way to do better science. And that means that astrophysicists and other scientists have been pressing NASA to reduce those proprietary times. And in fact, starting in the next cycle of Chandra observations, that proprietary time will be reduced to 6 months. Ideally, we want no proprietary time to exist. And a bunch of people, including myself from the Chandra side, are pushing for that to happen. And so we hope that in a few years' time, Chandra data becomes public as soon as it's observed, and the only merit of the observer will be to have the idea to observe those sources. But I think the more we do in open science, the better. Anyway, but the Chandra archive contains all the observations that Chandra has taken from the beginning of the mission up to yesterday. Well, no, that's yesterday, because of the proprietary time thing. Up to 1 year ago, basically everything that is public you can find in the Chandra data archive, and we have a page where you can retrieve information, and that's called the Chandra Chaser. In fact, I'm going to share my full screen now, because I think that's better. So if you actually go to a web page and you do a Chandra Chaser, then you'll see the Chandra data archive. Esteban, are you guys seeing this? I guess you are, right? The web page I just opened.
Yes, we are seeing your full screen at this point.
So this is basically a very quick service that you can use to retrieve Chandra observations. So it's web-based, so you can do it from your living room or from your university or wherever you are, and you can right away get data, Chandra data, from taken any time between 1999 and 2020. So that's excellent news. And there's ways in which you can do that. You can do that by coordinates. For example, you can do a cone search. A cone search is basically you select a location in the sky and a radius around that location, and then Chandra will give you all data that falls in that region that you've defined. You can also do that using a target name. So I don't know, for example, M87, it would be an interesting source. Then you resolve its name, and here you see that the coordinates get resolved. And then you can right away do a search. But before we do that, note that you can also do the search by observation ID. So basically, every time Chandra performs an observation, the observation gets assigned an ops ID, an observation ID. Basically, that's the sequence number that defines which observation was, in which order that the observation was taken. But you can also use the proposal title, the start date, the date when the observation was made, etc., etc. And you can also select instruments. So, for example, you could try to restrict your search to only HRC observations. And for example, if there were observations that were joint projects between Chandra and other telescopes, you can do that here. So let's try, for example, doing that M87 search only for HRC observations, see what we get. So when you do that, you've resolved the name already, and now you do search. And what's going to happen is that you will get a list of HRC observations for M87 in different observations. So you see here that you have different ops IDs, that those are different observations, namely different pointings that were made with the telescope in this direction. And of course, here we're only seeing the HRC ones. And then you have the exposure time, the target name, the principal investigator that requested the observation, the date, etc., etc. So you have all the observation here. And you can download them, and I'm not going to do the whole thing because depending on your speed of the internet, this can take some time. But basically, you can select the primary or secondary packages. You would usually be interested in the primary packages that give you basically the finally reduced event files. So those are the ones that you typically start with to do your science. If you're interested in earlier versions of the data before the calibrations were made, etc., you can select the secondary package. But actually, primary package is typically what you need. Or you can also do a custom selection here. Then you can select, for example, specific types of files. But for starters, what you would want to do is you want to get the primary package that will probably get things like, for example, the event files. And those are the things. And so you can select which of these ops IDs you want. Then if you add the products to the retrieval list, then you get here which ones you're asking to retrieve. And then when you do retrieve products, it will actually tell you, it will give you a link, and that link will tell you where. So this is just a link where your data will be after a few minutes. Actually, if I link on it now, maybe it's already there. So it's already there. So it's a tar package. You can just right away download it, and then you'll have your data. So that's the first way in which you can access the Chandra data products. Another way is, for that I'm going to go back to my presentation here. And another way in which you can do that is by using the Chow tools. So Chow is the Chandra, well, I remember Chandra Interactive Analysis something. I don't remember what the O stands for. As you can tell, it was first created by Italian people. That's why they wanted that particular acronym. But it's basically a package that allows you to do that. So among the installations that I requested Esteban to make for this, there was a version of Chow that hopefully is installed in your machines. But even if not, it's pretty easy to install. If you go to Chandra Chow and you look for a download and installation, there is actually a Conda. There is a Conda version that I recommend you install. If you all work with Python, then you can do a very easy installation in your own laptop for Chow. And one of the tools that Chow has is, so once you've installed, you can go to your terminal. For example, let me see if I can do that. You can go to your terminal here. I have many terminals open. Forget about the images that I will show you later. But suppose you're working on this terminal here, and then this one, you typically activate an environment where you have Chow installed. So in my case, that environment is called Chow 4.12, right? And then you already have the tool from Chow there. So you can do download. You know, the instruction I was showing you here. Download Chandra Ops ID. You see. So it recognized the command. You see it here. Sorry, it's a little bit small. But basically, with that command, you can say Chandra, download Chandra Ops ID, the number of the Ops ID, and then the type of file you want. In this case, the event file that is called the event file 2. There's event file 1 that is before calibrations. There's event 2 that is typically very good for science. And there's this event 3, which is the level that we've created to generate the Chandra source catalog. The Chandra source catalog is the top layer of analysis that we've performed on Chandra data, and it also has a very nicely corrected event 3 file.
Juan,
yes,
sorry, excuse me, I interrupt you. It is a little bit small, the font that you're showing us right now. Is it possible to put it on, increase the font size or something like that?
I actually don't know how to do that on Quartz, but let me see if with the terminal here, it's better. Maybe I can increase the size here.
Control plus, yeah. There
like
you go.
that. Is that better?
Well, it's a bit better. Not.
But
If you can make it even bigger, I think people will appreciate it. There you go, something like that. Yeah.
See it now?
So
okay.
Could you please repeat the lines that you mentioned it before, if it's okay?
Okay. Yes. Let me go to a proper directory here. So I'm going to be here. I'm gonna make a directory here called data, and I'm gonna go there, and I'm going to activate here my Chow environment, and so I can do download Chandra Ops ID. So this is basically a tool in Chow that allows you to and I'm going to delete the rest of it. So here, download Ops ID, as you see in the presentation here, you only need the observation number and the type of event. So the type of file. So if I say 12020, 12020 is an observation of the Cassiopeia supernova remnant, an ACES observation of the Cassiopeia remnant. And then I say event 2, then what should happen is that the system will download the observation in the current directory where you're living. And again, this might take some time depending on the speed of your internet connection, but basically that's how you do that. So you use that tool to download the data, okay? So once you have your data down, you can do anything you want to it. So you have an event file that you can, for example, visualize using DS9. DS9 is the visualization tool that was also created for the observations of Chandra. So that's actually what you saw before here. So you can have, this is actually the same Ops ID that I just created. So if you basically open a DS9 region, a DS9 session, then you can basically load the event file. And remember I told you that event files were not images. Well, that's actually the case. But what actually happens is that the DS9 software will kind of beam those events in space, and it will produce the images. You see this, my internet is a little bit slow, so this is only downloading it, but I had already downloaded it here. And in fact, I'm going to cancel this download because I'm afraid it's going to take a bunch of my internet band. So this is how you would visualize an event file in DS9. So DS9, that is part of Chow, by the way. So if in a terminal you type DS9, enter, then this software will appear. And the only thing you have to do is, for example, you can create a new frame that is here, and then you can file open, and then here is where you have saved your image. This is the event 3 file in this case, so you can double click on it, and then the event 3 file will eventually appear here, and you see it there. This is the same one I actually have here. So let's go to only that one. Here it is. So this is my event file, and you can do the typical things you can do in DS9 with things. You can change the levels to very visualize. So, but this is a supernova remnant. This is the Cassiopeia supernova remnant, and what you see here in the center is the central source, basically the neutron star that was left after the explosion of the supernova, and everything you see around it is the image I show you in the slides. And of course, one of the cool things that you can do here is, because you actually have the energy of every single photon. I mean, this is an extremely bright image. You have many counts. The value that you see up here, where it says value, is actually the number of counts, the number of individual detections you have in each pixels. And you see that in some cases you have like 200 or over 200 pixel counts, which is quite bright for an extended emission in X-rays. I mean, X-rays are very scarce. They are not very easy to detect. So this you can do, and you can see where the object is brighter. But you can also, for example, try to limit yourself to only certain energies. So if you want to do energy binning, you can do bin filter, and you can say, okay, I want to bin my energy between 500 electron volts and 1200 electron volts. That would be the soft band, and apply that. And what you'll see is that your image will change and will only show you now those photons within that energy range. So now you see here only the soft energy, soft X-ray photons between 500 and 1200 arc seconds. So this is how you would visualize your event file. And again, there's nothing you cannot do from here. You can, for example, get photometry. So you could select a region and measure the photometry, etc., etc. And I'm not going to do all of those things, but because we will talk about spectra and other things later. But I just wanted you to be able to visualize an image extracted from Chandra. And you can do this for any field, any OPS-ID. And as you saw in Chaser, you can select by coordinates, you can select by object name, etc. So if you're interested in star formation and you want to look at the Orion Nebula, then you will go to Chandra Chaser. Let's do it together. You will go to Chandra Chaser, right? Again, the beginning of this page. And then you will type in target name. You will say, okay, Orion Nebula, M42. And now I only want the ACES images. And I've resolved the name. So give me all the ACES images of the Orion Nebula. So you see there's a lot of observations of the Orion Nebula. And you can take any of these, download your event file, visualize your images, do photometry, etc., etc., etc. And again, this is not a course on photometry or anything like that. So I'm not going to actually show you how to do that. But those of you who've done photometry in the optical will be familiar with that. You can select a region around the source and measure the light that comes from it. So I just wanted to give you the ways in which you can actually access the information. The other thing is you can use the Chandra source catalog. And for that, let me go back. And I realize I only have 10 minutes left. But I wanted to introduce to you the Chandra source catalog. And the Chandra source catalog, as I said, is the upper layer of the Chandra data processing. So basically what we've done in the Chandra source catalog is we've taken all of the observations that Chandra has taken do stacking. So for example, if Chandra has observed in more than once the same location of the sky, we combine the observations of the same region of the sky to improve sensitivity. We detect all the sources in that field. So not only the target of the observation, but all of the serendipitous sources in that observation. And we detect the source and estimate all the properties for that source. And those properties include things like the photometry, how much is the X-ray flux, how much is, what are the spectral properties, for example, what are the hardness ratios that I will talk about later in this lecture, what is the variability of that source. We also have, in the Chandra source catalog, we also have the data products. So we can extract the spectrum you see here in the bottom left, the spectrum of a source. You can actually get the spectrum of a source in the Chandra source catalog. The hardness ratios that are basically a summary of the shape of that spectrum, and the variability, the light curves. You can see if sources are varying in time in the X-ray flux. So this is basically, we've done all the work for you in the Chandra source catalog. If you just want to do the science, you could take any source in the Chandra source catalog, and we have about 317,000 sources in the sky. You see a visualization of all the regions where Chandra has taken data here. And by the way, the red big spot in the center is the galactic center, where the supermassive black hole in our galaxy lives. And of course, we've taken a lot of observations of the region. You will basically be able to take any of the detections here and actually get data. And the notebook I will share, and I think I will only briefly show you the notebook in the last 10 minutes, will show you how to access all the sources from the Chandra source catalog. So you will have every single detection that has been done with the Chandra source catalog. You can get the properties for it and the data products. So the data products can be the spectrum of the source, so the distribution of energy of the photons, the light curve, and many, many other data products that we have for it. So let me show you how to access the Chandra source catalog. There is this nice software called CSC View, right? And I'm going to actually close CSC View for a second, and I'm going to reopen it again because I want you to and I believe I had also requested Stevan to install it. It's a very easy installation. If you go to the CSC2 page, the Chandra source catalog, we have and I think, unfortunately, my internet is so slow today that it's taking a while to do things. But you can, if you go to how do I access the Chandra source catalog here, the first link you'll see is the CSC View application, and you can easily download it. It will take a minute to download it and install it. And then you search for it and you open it. And this is what you'll get. So this is the interface that will allow you to do exploration of the Chandra source catalog. So anything that you want to get from Chandra that relates to a source, for example, the image of a source or the spectrum of a source or the properties of a source, you can get from here. And the way you do that is here you have the different releases of the catalog. We are currently in release 2.01. Early next year, we will start production of version 2.1 of the catalog. That will be an enhanced version of the catalog with more observations taken more recently. And then you go here to search. And here you will have a really rich interface that will allow you to do specific searches. So basically what you have in this result set is all the properties, X-ray properties of the source. For example, the flux, how much X-ray flux there is in a particular source, the errors in that flux, and we will talk a lot about errors in the incoming lectures. For example, here you have only put the fluxes of X-ray sources, but in principle here you have a whole list of many different positions, properties that you could select and actually drag. So for example, if you were interested in the significance, which is already here, you could just take it and drag it here. But it's already there, so it's not gonna reput it. But you can select any of the properties in X-rays and just drag it into your result set. And you can also do search criterion. So for example, you could do a consearch, limit your search, for example, to only regions close to M42, again, the Orion Nebula. So let me make this a little bit larger, M42. Then you have the resolver, and you say, give me all the sources that are close to N42 within 1 arc minute, right? And if you do that and then do search, again, it will take a little bit because of the internet, but what you will get eventually here will be the list of sources that live in that region of the sky, and with all the list of properties that you had in your result set. So for example, the fluxes, if you had included also the hardness ratios, etc., etc., etc. All right? So let's wait for it to come up. In the meantime, let's look at the notebook. So the notebook is just a much more interactive way for those of you who are more into the Python world. I wanted to show you how to do the download of Chandra data using the Python interface, the Jupyter notebook. So I am assuming that most of you will actually be familiar with IPython notebooks. But this notebook that I have in GitHub, and you should have the link for this notebook, so you can download the notebook, and you should have everything installed in the university machines that will allow you to do this run. And I will only take 5 minutes now to briefly show you how this works. So you can go yourselves throughout this notebook, but this is a notebook that is designed for you to interact with the Chandra source catalog by getting information that you can straight put into your IPython structures, and that you can use to do, for example, things like cross-matching with other catalogs, if you want to do machine learning, etc., etc. So basically, what is shown in this notebook is a number of things. I show you how to use a const search from your Jupyter notebook to actually perform a search like the one I just performed in CSC view, which, by the way, has, by the time I was talking, it has finished. So it has here my list of sources. So the list of sources, the Chandra sources are identified as 2CXO. That means that this is version 2 of the catalog. And the name of the source has to do with the coordinates of that source. And then here are all your properties, and you can download this table and put it in your favorite format. If you use TopCat, you can also use this send command in CSC view to send it to TopCat, so you will have this table ready for being plotted, etc., in TopCat. But I wanted to focus. If you have questions about CSC view, please feel free to ask me this week. I will mostly be focusing, however, on the Jupyter notebooks, because I find them a more interesting way to interact with the catalog, and it's probably more akin to what you're used to. So this notebook, which I will not have time to review today, so we will continue tomorrow, but this notebook shows you how to use a const search in order to get sources from the Chandra source catalog. It will tell you how to do more complex searches. For example, if you want to do searches that contain specific properties and contain properties that were done on a particular observation of a source, because again, source can be observed more than once in Chandra data. So you can, for example, you're interested only in the properties that were derived for a single observation, you can do that. I will also show you how to cross-match the CSC2 catalog with other catalogs and visualize the results. And I will show you how to download that data products from CSC view. For example, if you want to do spectral analysis of sources, I will show you how to download the spectrum of the source, and we will actually be doing some spectral fitting of the spectra when we talk about spectroscopy later in these lectures. But these are all the things that will be covered, and I am afraid it will not be today. So I will start the practical session tomorrow with this notebook, and I will walk through the different aspects of how to get your tables, how to plot your results, etc., etc. So by the time we are in the session tomorrow, you'll be able to follow the notebook yourself and do all the cool things that you can do with Chandra data. So feel free to experiment with it a bit during today, or with CSC view, or with Chao and DS9. And if you have any questions, you can ask me either by email or tomorrow during the session. So I'm gonna leave it there because I know some of you have to leave today. I hope this was a good introductory talk. In tomorrow's lecture, we're gonna be talking about the aspects of probability and statistics, and how we use concepts of statistics to study X-ray data, and how we use concepts of Bayesian statistics to do photometry of X-ray data. And I will introduce you to some cool tools to do Bayesian inference using Chandra data to estimate fluxes and hardness ratios of particular Chandra sources.
Okay, Juan, thank you very much. Yeah, for all the participants here in the chat of this YouTube, we leave you the installation instructions, at least the webpage for the installation instructions, the GitHub from Juan Rafael, where he placed all the notebooks and the material you will need. And we invite you to follow the instructions of the installation for the libraries that you will need for the rest of the week for Juan Rafael exercises, because it can take a while to install some of them. So just try to do that during the rest of the day so you can have everything ready for tomorrow. Even though we will leave you in the webpage of the school a small bash that I created last week in order to facilitate a little bit the whole process of the installation. So thank you very much. Thank you, Juan Rafael, for the introduction today. It was great, in fact. I learned a lot. So let's see you tomorrow, and thank you very much.
Thank you all. See you tomorrow.
Bye.